Yeah, my answer there is not generating 20 out of 10. It's very concerning about galaxies. Yeah. We should start. Hi everyone, it's my pleasure to introduce Pratika Dayal from Rijksuniversiteit Groningen. She's going to talk today.
You pronounced that
Right.
Whoa! You've been practicing.
I practice.
Dutch.
No, they're cheesy. From Rijksuniversiteit Groningen, if you wish. Yeah, she's an assistant professor there, and before that she was an Addison Wheeler Fellow at Durham University, a postdoc fellow in Edinburgh, and a postdoc fellow at the Leibniz Institute in Potsdam. And she did her doctorate at CITA in Trieste in Italy. Well, Pratika will talk today about the emergence of galaxies in the first billion years. And well, take it away. Thank you very much.
Thank you very much, Brett. Okay, so good morning, everyone. It is really a great pleasure and also a privilege to be here to talk to you about some of the extremely exciting results that we're getting from early galaxy observations and how these fit into a theoretical context. And what I'll try and do is really give you a global overview of what these are implying for three different things: for the epoch of reionization, what they are implying for cosmology, and what they imply for the era of gravitational wave astronomy. If you have any questions, please feel free to just ask me during the talk. Yeah, that is perfectly okay, and we can have a chat about it. Okay, so before I go into the details, I would really like to acknowledge the work of a number of young people going from undergraduate to master students, PhD students, and postdocs. So this is an evolving timeline of our group, also during the COVID era. And these are basically the people who have really had a major contribution in building the theoretical models that I'm going to show you today. I am also going to show you results on behalf of a number of different observational collaborations. So I'm the key theorist on a number of collaborations, including the ALMA Rebels team, on a number of programs from the James Webb, which are basically Uncover, Panoramic, Prima, and Cosmic Spring. And a lot of what I'm going to show you is also the theory that we are trying to establish for the forthcoming era of SKA and Euclid, and how we're trying to fit all of these observations together to create a holistic view of the universe in the first billion years. So before I jump into the talk, let me start by showing you our cosmic timeline, which has been really painstakingly built over decades of observation. So what we understand now is that our universe started with something called the Big Bang, which was followed very soon after by a period of accelerated expansion called inflation. During inflation, the universe was basically expanding. After inflation, kept expanding, and as it was expanding, it was cooled. Finally, at a redshift of about 1100, which is roughly 400,000 years after the Big Bang, the universe for the first time was cooled enough that electrons and protons could combine to form neutral hydrogen. And at this point, matter and radiation get decoupled, giving rise to the CMB, which is our earliest view of the universe in its entirety. Now, the period after the formation of the CMB is known as the Dark Ages in the history of the universe. And this epoch, which can last a few 100 million years, is called the Cosmic Dark Ages because at this point, all that is happening is that dark matter is trying to collapse to form halos, but baryons have not yet started to fall inside these halos, cool, and form stars. So really, the only photons you have at this point are the photons of the CMB, which are now basically free streaming throughout the universe. So these cosmic dark ages come to an end at a redshift of 30 or 13, whenever the first galaxies start to form the first stars. And at this point, these first sources, the moment they turn on, they do something really important. They are the first sources of light in the universe. They are the first sources of metals in the universe. And most crucially, they produce the first photons that can start breaking up or ionizing hydrogen. And this marks the rise of the era of cosmic reionization. Now, of course, at these early stages, the universe is 75% hydrogen, roughly 25% helium. But for the purposes of this talk, I will ignore helium and only focus on hydrogen reionization. So in terms of a global context, when these first sources turn on, so those are these little yellow dots, these first sources will start ionizing the regions around themselves, which you see marked by these grayish patches. As more and more sources form close to each other, these regions start growing, they start overlapping, and this is generally what is called the overlap phase of reionization. Finally, at some point, we think we had enough sources of ionizing radiation such that these ionized regions could cover all of the available volume of the universe, and at this point, we say the epoch of hydrogen reionization is complete. This happens somewhere by a redshift of 6 to 5, somewhere within the first billion years. What is really crucial to note is that this is really the last phase transition of all of the hydrogen in the universe in its entirety. Once this hydrogen was reionized, it has since then remained reionized for the next 12.5 billion years. So the one thing that I would really like for you to take away from this plot is that reionization was an extremely, extremely patchy process. It lasted a billion years, and what we are trying to do as we enter the era of 21 centimeter cosmology is really to track down this patchy progress of reionization, or what we call the patchy topology of reionization. So I would argue now is really the golden age for observing these early galaxies. So a little bit of history, when I was doing my PhD, we had one galaxy candidate at a redshift larger than 7. And so we were, of course, building theoretical models to try and understand these objects, but we had no observations to actually baseline our models to. And in the 13 years since I did my PhD, the field has really exploded, I would say, because now we have more than 10,000 galaxy candidates at redshifts larger than 6, 1,000 of which are spectroscopically confirmed out to redshifts of 13. And this has been driven to a large extent by the James Webb. And so now what we can finally do is we have enough galaxies to really start building demographics. So we can start asking things like, how many galaxies do we have as a function of luminosity per co-moving volume in the universe? So this is nothing but the distribution of luminosities or the luminosity function. We can chart out its evolution out to a redshift of 15. We can look at how many total stars are forming per co-moving volume of the universe. So this is nothing but the evolution of the star formation rate density of the universe. We can also measure masses with ALMA and with James Webb. So we can also ask how many galaxies do you have of a given mass per co-moving volume, which is the stellar mass function. We can look at how much total bound mass we have at any given cosmic epoch, the stellar mass density. And especially with ALMA, we are able to really probe out the dust masses, and with James Webb, we can probe out the metallicities of these early systems. So as of now, we have metallicity estimates of galaxies out to a redshift of 13, which was really unthought of even 2 years ago. And finally, something that I'll show you is that the James Webb has really yielded entirely new populations of black holes, which were really unexpected. And so for the first time, we can start to look at black holes and their emergence within the first billion years. So of course, these fantastic observations have spawned a number of open questions, such as, so what exactly were the physical properties of these early systems? How was galaxy assembly dependent on the local environment, if at all? What did these early galaxies evolve into as a function of cosmic time? When and how did these early sources reionize the universe? Something that I will try and show you that is extremely important is that reionization has a feedback effect on galaxy formation. And so the question is, what was the impact of this reionization feedback on the early galaxy populations that we are trying to observe? What was the role of black holes in early galaxies and reionization? And because we have black holes, we expect they must have merged. So how many event rates do we actually expect from the early universe in the era of multi-messenger or gravitational wave astronomy? And finally, what I'll also try and show you very briefly is how these signals can actually tell us also something about cosmology. And here I mean something about the nature of dark matter in terms of warm dark matter. So I'm going to be using a lot of data from ALMA and James Webb to baseline our models as we look towards the era of Euclid, SKA, and of course LISA. So continuing on the complexity of the problem, we're trying to model galaxies going from parsec scales at which star formation takes place to these extremely large hundreds of megaparsec scales on which the cosmological process of reionization takes place. And so this is really a multi-scale process. This has required using different kinds of tools or different kinds of techniques to try and address specific problems. So in my group, we use all of the different techniques available, going from really just analytic formalisms to semi-analytic models, to semi-numerical models, to hydrodynamic simulations. And I will just try and give you a flavor of where each of these kind of tools or techniques are most relevant as we go throughout the talk. So this brings me to the actual structure of the talk, which is I will first try to talk to you a little bit about the emergence of galaxies in the first billion years and their implications in the era of 21 centimeter cosmology and for reionization. I will then briefly show you how these early galaxies can also be used to say something about the nature of warm dark matter. And finally, the puzzle of these black holes which are emerging in the first billion years and what they imply for gravitational wave astronomy. So let me move on to the first part of the talk. And just to show you, this is actually one of the first images that came out of the James Webb. So this is the James Webb Deep Field. And so all of these, many of these tiny things that you see are actually extremely, extremely high redshift galaxies. And so this was really revolutionary when it came out. This was just to make sure that the point spread function was working. But then, of course, with this image itself, people found a number of the highest redshift sources we have detected so far. So let me start by showing you what is the key physics that is going to drive the process of reionization. So in its most basic sense, in a global sense, when we model reionization, what we are trying to do is to figure out what fractional volume of the universe is filled with ionized hydrogen and how this evolves as a function of time. This is driven by naturally a source term, where the first part of the source term is how many ionizing photons are your sources actually producing per co-moving volume. This could be either because of star formation or from black holes, it doesn't matter. What is the volume density of the production rate of ionizing photons? The second term is the escape fraction, and you will generally just see it written as F escape, which can be confusing because there are many different escape fractions we talk about. But here, what we mean is galaxies are really complicated environments. Most of the ionizing photons that are produced within the galaxy do not make it out of the galactic environment because of gas, because of dust. And so there is a small fraction of these ionizing photons that can actually come out. So the source term is what is the volume per unit volume, how many ionizing photons can actually emerge out of bound systems. So this is your source term. And there is also a recombination term, which is driven by the fact that if you have regions that are extremely dense, they can recombine on short timescales. And so you may have to reionize extremely dense regions multiple times before they are finally reionized. So let me show you what are the key problems with this extremely simple global process. So the first thing we need to do is we need to understand how many ionizing photons are produced per co-moving volume as a function of redshift. Let me make an assumption that most of these photons come from star formation for the sake of simplicity. So basically, you can just say, well, how much star formation do I have per co-moving volume as a function of redshift? And this can be just a proxy for how many ionizing photons you're producing. So here, what I'm showing you is all of these are observations. The gray points are all of the observations that we had pre-James Webb. The red points are all of the star formation rate density observables that we have post-James Webb. Now, what you can clearly see is that observations seem to agree about the star formation rate density out to a redshift of about 8 or so. But as you go to higher redshifts, as of now, the star formation rate density could fall off as steeply as 1 plus z to the power minus 11, or it could fall off as shallow as 1 plus z to the power minus 3.5. The data from James Webb, as you can see, sort of lies on the lower end, but these are really a few observed data points. We are trying to confirm more and more galaxies. But what I want you to take away from this plot is that as of now, the star formation rate density evolution, especially at high redshifts, remains really poorly understood. So the first part of the source term, how many photons are galaxies actually able to produce, really remains poorly understood, especially at redshifts above 10 or 12. The second part of the source term is how many of these photons can actually escape out of the galactic environment. So here, I'm showing you a plot of the escape fraction as a function of redshift. Again, these are all observed data points. I'm not showing you theory because theory is even more complicated to interpret. But what you can see is that basically, if you look at very similar objects at a given redshift, the escape fraction can be below 10% or even below 1%, or as high as 100%. So as of now, there is no consensus on how many ionizing photons can actually escape out of galaxies. So this is just to tell you that the source term for reionization remains really poorly understood in the first billion years. A complexity is induced by the fact that reionization itself can have a feedback effect on galaxy formation. So here again, the same illustration that we have already seen. All of the blue patches that you see are neutral hydrogen, where you can assume that the temperature is the ambient CMB temperature. So at a redshift of 9, for example, the temperature of this neutral gas should be of the order of 27-ish Kelvin. In regions that are ionized, so these gray patches, however, the temperature can rise up to 20 or even 30,000 Kelvin, depending on what are the sources which are driving the process of reionization. So now imagine that you are a low-mass galaxy, which is sitting in one of these ionized regions. If your virial temperature is of the order of 20 or 30,000 Kelvin, you are embedded in a bath, which is the same as your virial temperature. Basically, what this means is that for such a low-mass galaxy, the gas can be either photoevaporated or heated enough that this thing will just stop forming stars. And so reionization can actually halt star formation in low-mass sources, which are really the most ubiquitous objects we have in the universe. And so this is what is called the effect of reionization feedback on galaxy formation. So here, I would just like for you to appreciate the scales that we have to go through from the kiloparsec scales on which galaxies are actually forming stars, out to the large-scale process of reionization. And just to give you an idea, for a convergence on the topology of reionization, on this patchiness, you need volumes which are at least 200 megaparsecs. So you have to go over 6 orders of magnitude in physical scale if you really want to model the interplay between galaxy formation and the large-scale process of reionization. Yeah, of course.
The way at which each bubble grows and so on, it seems decoupled between bubbles until they merge.
Oh yeah, sorry, this is, no, so it's not. Can I just show you this in 1 second? And this is really just an illustration. So yeah, let me just show you. So this is a super nice question. In 2 slides, you will have your answer. Okay. Okay, so well, the whole problem is that this multi-scale problem of reionization, which goes from the parsec scales of subparsec scales of galaxies out to megaparsec scales, has really spawned a multitude of theoretical efforts to really try and understand galaxy formation during the epoch of reionization. So this is work that we did in 2018, and there are already a number of other fantastic models which have appeared. So the idea is that there are a number of small-scale models where people are trying to model individual galaxies or scales of 20 to 40 megaparsec to really look at the kinematics, the dynamics, and the internal properties and the growth of galaxies. But these volumes are too small for you to be able to converge on the topology of reionization. A second set of models is what we call intermediate scale models, a few hundred megaparsecs. These are mostly looking at galaxy formation. There is some coupling to reionization, but generally it's not self-consistent. But again, this volume is really small to really converge on the topology of reionization. And so for the process of reionization, there are a number of large-scale models which go up to half a gigaparsec. So here you would converge on the topology of reionization. But then naturally, they don't have the resolution to really track the formation of those tiny systems which started the process. And so to solve this issue, we created our own model, which is called Astreus, which is a 230 megaparsec simulation in which we have really tried to couple together the processes of galaxy formation and reionization. This is a semi-numerical model. And so, well, let me just acknowledge the work of this entire team who were instrumental in driving this process. And so the idea is as follows. We start with an n-body simulation, which is 230 megaparsec, 3,840 cube particles. So you can resolve down to 10 to the 8 solar masses in terms of halo mass. So from this n-body simulation, which starts at 100, we can follow it all the way down to a redshift of, we stop at 3. For all of the halos that you have here, you can see how they are assembling with time. And so then you use a semi-analytic model of galaxy formation, which is called Dayal, to put in all the key processes of gas accretion, gas cooling, star formation, even black holes, feedback from star formation, black holes, metallicity enrichment, dust, etc., so that you have all of the physical properties of your galaxies. For each galaxy, you then compute how many ionizing photons it is able to produce. You have to assume escape fractions. I will just show you in a second what the impact of that assumption is. To be able, and then we use CFOG, which is a semi-numerical code for reionization, to create our ionization fields at every step. So now imagine this is at a redshift of 10, for example. So you would use these ionization fields at the next snapshot to say which kind of galaxies are suppressed because of reionization feedback. So this is a fully coupled model for galaxy formation and reionization. And this is what we have been using heavily to interpret the data that is emerging out of James Webb. And these kinds of models are also really important because they form the data sets that you need to train for the next generation instruments. So for example, for the SKA, we need some kind of theoretical models to tell us if we see something, what does it actually imply about the underlying sources or about the topology of reionization. And so these are the sorts of models that we're building to try for these next generation physics.
And the reionization feeds back the same analytics for the galaxy formation. Okay.
So let me just show you what happens. So this is basically now the progress of reionization in this framework. If you look on the bottom left panel, this is the redshift. The black color shows you neutral hydrogen. Pink dots are galaxies, and white patches that emerge are going to be your ionized regions. So once I start running this model, you can see as time goes by, more and more sources are emerging. These could be either star-forming galaxies or these could be black hole hosts. And as time goes by, they are producing these ionized regions which grow and which start overlapping. But what I want for you to note is that reionization actually starts in dense regions where you have a lot of galaxies, where these ionized regions can really start overlapping. So it starts in dense regions and percolates into underdense voids. But now you would say, well, okay, so which are the key drivers of reionization? So here, what I would already like to anticipate is that the escape fraction really remains an open problem. So what we're doing is running these sorts of models for different assumptions on the escape fraction. So on the top panel here, we go from a redshift of about 10 to a redshift of about 6.5. The dark blue color shows you neutral hydrogen. Light patches show you show ionized hydrogen, and this is the degree of ionization, which we can also follow. In this top panel, we are assuming that the escape fraction decreases with an increase in mass, which means the escape fraction is the highest for low mass objects. Low mass galaxies in this are the key drivers of the reionization process, which is the standard view as of now. But then you can also do another calculation where you say, what if the escape fraction increases with increasing mass, which is also something that has been observed in a number of observations. And so here, high mass galaxies would be the key drivers of reionization. So remember, galaxy formation, we have the same galaxy formation and the same underlying density field in all of these different models. So for example, at redshift 10, the only thing that is different between these two simulations is the escape fraction. What you can immediately start to see is that the topology of reionization looks very different. It is much more homogeneous when low mass, homogeneously distributed sources drive the process, as compared to when high mass, highly biased sources drive the process. The patchiness of reionization actually increases. And so this is a key diagnostic that you can actually apply to try and figure out which galaxies are the key drivers of the reionization process. But then I just showed you, so this model is calibrated against all of the data that we have up to a redshift of 10. So we can, of course, when the data came out from the James Webb, we wanted to see how these models would compare to these fantastic new observations that we have. So here I'm showing you the number of galaxies per co-moving volume as a function of their absolute magnitude. So these are bright objects, these are faint objects. And the moment James Webb data came out, it showed us something really puzzling. So there seems to be an overabundance of bright galaxies at redshifts larger than 10. So here I'm showing you the luminosity function, or the number density that was inferred at redshifts of about 11-ish. Theory would predict number densities which lie here. So for example, they are compatible kind of with this intermediate luminosity object, but this high luminosity object is orders of magnitude higher in terms of number density than what theory was predicting. We even had a galaxy candidate at a redshift of 16.5. This is the number density that was measured. This is what different theoretical models would predict, including Astreus. So you can see there is some sort of a problem here because there is a severe overabundance of bright galaxies as you go into the first billion years of the universe. And just to anticipate, this line that we made is basically just taking a halo mass function at a redshift of 16.5, assigning every halo baryonic to dark matter ratio, which is the cosmological ratio, allow all of that gas to instantaneously form stars. So this is sort of the upper limit to how many galaxies you could observe at a redshift of 16.5 if everything was exploding instantaneously. So now you can see this galaxy is really hitting against this upper limit, right? Which poses an enormous problem. And so there has been a lot of discussion in our field that while most models are in perfect agreement with observations below redshifts of 10, there is a severe overabundance of bright systems. And so there are many different solutions which you can invoke, including the effects of dust are becoming less and less relevant at high redshifts. I will just show you in a second why we care about dust. It could be that the initial mass function of stars evolves as a function of redshift, and everybody is just using the usual saltpeter or Chabrier IMF that we use at low redshifts. These early galaxies could be extremely bursty in terms of their star formation, so we are really only seeing those galaxies which are at the tip of the iceberg, so to speak. Maybe these systems could have some sort of a contribution from black holes, which is boosting up their luminosity above what you would think is possible purely from star formation alone. Or many of these things that we're looking at could actually just be low redshift interlopers that we are misidentifying as high redshift candidates. And indeed, this was found last year. So this redshift 16.5 candidate is actually at a redshift of 4.9. And the reason is that this has extremely strong O3 plus H beta nebula emission lines, which were really unexpected. And so this has biased our traditional methods of looking for the Lyman rate for these high redshift systems. So as we proceed, this is one of the key aims to really try and figure out which of these early galaxies are really high redshift objects versus low redshift interlopers. And this is also going to tell us a lot about the ISM properties of these objects in terms of nebula emission lines. The second problem that has emerged, and here I would like to acknowledge these junior colleagues who have led the work, is that these early galaxies are extremely, extremely dusty. So this is work that we have done as part of the Rebels ALMA collaboration, where we targeted 40 really UV bright objects at a redshift of 7. And what I'm showing you here is just the dust mass plotted against the stellar mass. The green points are the data we had pre-ALMA, and the blue points are what is emerging from ALMA. The shaded region that you see shows you the dust mass that you would infer if you would assume two different dust temperatures of 30 Kelvin or 80 Kelvin. So now the problem that you can immediately start to see from this plot is all of these lines that you see are theoretical models of how much dust can be present in a galaxy as a function of the stellar mass, no matter which kind of process you include. So here, this is just production. This is astration plus destruction. If you include the effect of brain growth, ejection, no matter which kind of processes you choose to include in your dust modeling, the dust mass always scales with the stellar mass. But when you look at the observations, these are extremely flat. So the dust mass is basically independent of the stellar mass. And especially for these low mass objects, we're finding dust to stellar mass ratios of 1%. This is higher than what we see in the Milky Way. But remember, the Milky Way has had 13 billion years to evolve. These galaxies have had 700 million years to evolve, so they do not even have asymptotic giant brown stars to produce the dust. All you can do is produce dust from supernovae. So this is a huge puzzle. Why are these early galaxies so dusty? So one solution could be that we are really underestimating the stellar mass of these objects, which was one proposal that was put forward, that if you assume galaxies had a constant star formation history, that would severely underestimate how much stellar mass they could have formed. So this is one solution that we have proposed. Because the other solution, theoretically, would lie in invoking some sort of a maximal model, which is this grayish line, the grayish shaded region, which we call our maximal thought experiment, where each supernova can produce one solar mass of dust. You cannot eject this dust, you cannot destroy this dust, but this dust should just keep growing in the interstellar medium on extremely short timescales of 0.3 million years. And these are all numbers which are pushing everything we understand about dust to its very limits. Okay, so we have all of these early galaxies. Many of them do seem to be dusty, but what does this actually mean for reionization? So the question, of course, is, could these galaxies that we're seeing reionize the universe? So this is work that I've done for the Uncover survey. which is a James Webb program. So here, let me show you the electron scattering optical depth as a function of redshift. This green shaded region are limits from Planck. If you consider all of the stars that we have so far, if you consider normal theoretical models, and for everybody who is interested, I'm not going into the details, but if you're interested, please ask me more about this later. So we have a full model of dust, and we actually link the escape fraction to this dust, because this is something that we actually observe at low redshifts. So assuming that there is a link between dust and the escape fraction, we find that basically the star formation that we have so far is enough to reionize the universe, so we can get the right electron scattering optical depth. Most of this contribution comes from star formation in low mass galaxies, so which are below 10 to the 9 solar masses in stellar mass. I'm sorry, these labels are inverted, so these are low mass galaxies. When you look at high mass galaxies, they don't make a huge contribution to reionization just because they are in general more dusty, which reduces the escape fraction of ionizing radiation. So you can also ask, are these, what does the volume filling fraction of ionized hydrogen actually look like? So this is the volume filling fraction as a function of redshift. All of the red points that you see are observational constraints from the Lyman alpha forest, from quasars, from Lyman alpha emitters. So it's from different classes of galaxies. And here again, what you see is that within this simple model where you have the galaxies that you have, you include their dust, you're able to reionize the universe by a redshift of about 5.2-ish or so, which is really well matched to what observations seem to be showing us. Again, this is driven by low mass star forming galaxies. High mass star forming galaxies have a very small contribution overall to the process of reionization. So this is to show you the global process of reionization. But now you would say, well, okay, but you told us reionization is really patchy. So how exactly are we going to probe the patchiness of this process? Which brings me to a class of galaxies called Lyman alpha emitters. As the name says, these are galaxies which are visible through their Lyman alpha emission line at 1216 angstrom in the rest frame of the galaxy. So the whole idea is as follows. Lyman alpha is really sensitive to absorption against neutral hydrogen. So if 1 part in 10 to the 5 of your hydrogen atoms are neutral, basically you have an optical depth of 1. So the idea is as follows. Let's say I have all of these galaxies which are embedded in a neutral IgM. Let's say I have this galaxy which produces Lyman alpha photons. The moment these photons come out of the galaxy, they will get scattered away because of interaction with neutral hydrogen. So this galaxy is not going to show up as a Lyman alpha emitter. But then imagine you have galaxies which are sitting clustered together, which can build a large ionized region around themselves. They produce Lyman alpha photons. If the region is large enough, by the time the Lyman alpha reaches the edge of this ionized region, it is redshifted out of resonance with neutral hydrogen. So some or all of these galaxies can become visible as Lyman alpha emitters. So the idea is that only clustered objects would be visible as Lyman alpha emitters in the initial stages of reionization, with more and more field galaxies or normal galaxies becoming visible in Lyman alpha as reionization proceeds. So this is something that we had postulated as early as 2010, and we were not the first to postulate this, but we were the first to find an observational the first observational evidence of this. So this is work that I did with Marco Castellano, where we found 2 Lyman alpha emitters, which are separated by 4 physical megaparsecs in the Bremer deep field. And we postulated that alone, these were not enough to build a large enough ionized region to be visible as Lyman alpha emitters. So we followed them up with the Hubble Space Telescope, and indeed, we found them clustered with a lot of other low luminosity objects, which are not Lyman alpha emitters, but they are star-forming galaxies. And so, what can we do with this as we move forward? So let me show you what the visibility of Lyman alpha emitters looks like, again, now in Astreas. So here, again, this is a redshift of 8, 7, and 6.5, and these are typical redshifts at which we find Lyman alpha emitters just because of the filters. And so what I want you to note again is that, again, the top panel is the situation in which low mass galaxies are the key drivers of ionization. And here, the stars, which might be hard to see, just show you the luminosity of the Lyman alpha emitter. So the bigger the star, the more luminous the galaxy is in terms of its Lyman alpha. So here, what I would really like for you to see is that Lyman alpha emitters are preferentially lying in ionized regions, especially in the initial stages of reionization. So exactly as postulated. As reionization proceeds, you can have even normal field isolated galaxies, which can become visible in Lyman alpha. This is the situation in which high mass galaxies drive the process of reionization. So you can immediately see that not just the distribution, but also the luminosities of galaxies, which are Lyman alpha emitters, look extremely different in these two scenarios. So essentially, the idea is that the visibility and the luminosity, crucially, of Lyman alpha emitters depends on the underlying density, which determines at which rate reionization is going to proceed in a certain patch of the universe. And the other key parameter that is super important is the escape fraction, which basically determines the topology of reionization, and also, therefore, what is the impact of reionization feedback on galaxy formation. So you could say, well, what exactly are we going to do with this? And this is something that we are doing as part of leading as part of the SK pop-up reionization synergy group, where the idea is really to create synergies with other facilities to really try and pin down the patchy topology of reionization. So here we have compared a number of different models, but qualitatively the results are really similar. So you can also just look at these colored patches. So this is for a universe which is half ionized. Here, this is 75% ionized, 90% ionized, and completely ionized. So this just shows you the fraction of hydrogen which is neutral. So here, what I'm showing you is the cross correlation between 21 centimeter and Lyman alpha emitters. Everybody knows the 21 centimeter emission is going to come from regions which are neutral, which, as I just showed you, are actually going to be anti-correlated with your Lyman alpha emitters. So wherever you have neutral hydrogen, you will just not have Lyman alpha emitters. So this correlation is the strongest when the universe is half ionized, half neutral, because this is the first time when galaxies can actually start transmitting enough luminosity to give you enough number statistics in Lyman alpha emitters. But there is a lot of neutral hydrogen that is still left. As more and more of the hydrogen gets ionized, the amplitude of this anti-correlation drops, because now, although many more galaxies are visible in Lyman alpha, the power in 21 centimeter is dropping faster. Finally, this correlation will basically settle to zero by the time the universe is fully reionized, because now almost everything can transmit enough luminosity to be visible in Lyman alpha, or at least transmit enough Lyman alpha luminosity. There is just no neutral hydrogen left to give you a cross-correlation signal. Crucially, this turnover scale actually tells you what is the typical sizes of these ionized regions which are hosting your Lyman alpha emitters. And so these are exactly the sorts of signatures we are looking towards as we enter the era of SKB. Very quickly, I would also like to show you how these galaxies are extremely important. They have important implications for cosmology. And so let me start with an extremely simple model. So this is the assembly of galaxies in the standard hierarchical lambda CDM model, where you say the mass of the particle is roughly 100 giga-electron volts. Time is moving downwards. So this is at high redshift. This is the merger tree of one specific galaxy. And this is all just illustrative, so you don't really have to care about numbers. But all we're trying to do is show that galaxies start off with small masses, and they merge through time to form larger and larger systems. And here, I really want to acknowledge the work of two undergrad students who were really crucial in motivating me to do this work. So this is what galaxy assembly would look like in our standard lambda CDM framework. Let me use a toy model of warm dark matter. So this is thermally decoupled relativistic particles, so really a zeroth order model. 3 keV mass. All that happens is that because these particles will have slightly higher velocities compared to the standard lambda CDM particles, they will just not clump on really small scales. Basically, this means structure formation gets delayed, and also you start off with larger halos, because small mass halos are just not able to bind in this sort of a model. If I invoke an even lighter particle mass of 1.5 keV, structure formation is delayed even further, and you would start with even bigger halos. So how can we actually use this to say to apply this to data? So what we have proposed is something extremely simple. In these three different cosmologies, so black is CDM, blue is 3 keV warm dark matter, red is 1.5 keV warm dark matter, purely analytic. All I did is I looked in a volume of 10 to the 3 co-moving megaparsec cube, which is a volume that is really easily, that can be studied with the James Webb. In these tiny volumes, you look at the number density of halos in different cosmologies. Assume every halo to have a cosmological ratio of gas to dark, of baryons to dark matter. Allow all of those baryons to form stars. This is the maximum stellar mass that you would get in any of these cosmologies as a function of it. So here, what you can see is in lambda CDM, you would keep forming mass out of redshift of 20. You stop at 18 in 3 keV, you stop at 12 in 1.5 keV. And here I'm showing you masses that we have actually measured from the James Webb. So you can see they're reaching really close. They're of the order of, we're already at about a redshift of 10. So if you can find objects at a redshift of 12, for example, it doesn't matter what their mass is. If you can survey many different patches of the sky, which is actually what is going to be done in these kinds of volumes with the James Webb, if you find any sort of stellar mass, it basically, if you start finding stellar mass in many of these patches, so if it's just one, it could be cosmic variance. But if you start finding stellar mass in many of these patches, basically you could already start ruling out something as light as 1.5 keV warm dark matter. And this is really crucial because it extends our constraints on warm dark matter to an epoch that we can really not access by any other means. The same thing can be done with signals, which are really from the era of what we call cosmic dawn. I really do not want to dwell too much on this in the interest of time, but this is just to show you the 21 centimeter signal that you might have heard of from the EDGES collaboration. So this is just a signal which comes from a redshift of about 16 to 20. And this is because at this point, so this is the signal is actually the differential brightness temperature of neutral hydrogen minus the CMB temperature. So the signal is negative because at this point, gas is colder than the CMB. And the spin temperature of 21 centimeter is coupled to the gas. You don't really have to go into the details. The point is just that this is exactly the signal that we had expected from the era of cosmic dawn. In CDM, you are able to reproduce this signal. So please don't care about the amplitude. So all we care about is the redshift. The key reason is that this signal is produced because Lyman alpha photons from some kind of star formation or maybe from black holes are needed to couple the spin temperature of 21 centimeter to the kinetic temperature of the gas. So in warm dark matter, in CDM, as I just showed you, we have enough photons to be able to do this even by a redshift of 20. So you can reproduce the signal. 3 keV is slightly harder because there are just not enough structures in place to produce enough Lyman alpha photons for this coupling. But in something as light as 1.5 keV, you just don't have any structure already in place by a redshift of 20. So these sorts of 21 centimeter global all sky signals will be actually one of the strongest constraints that we will have on the nature of dark matter. Unfortunately, this 21 centimeter signal from EDGES has been ruled out by the SARIS experiment. Very happy to talk more about this later, but in the last 10-ish minutes, I would very quickly like to tell you about black holes in the first billion years and what these are implying for the era of gravitational wave astronomy. So for this, I'm going to use a slightly different model because black holes we know are rare objects. And so we need to model really large ranges in terms of masses. And so here, I'm going to use a semi-analytic model where we can explore halos between 10 to the 8 to 10 to the 14 solar masses between a redshift of 4.5 to 40. Again, the same methodology. You start from a redshift of 4.5 and you start creating analytic merger trees for each halo up to a redshift of 40. And then you start from high redshifts, putting in all of the key physics or the gastrophysics which you think is driving these early galaxies. So this includes stellar and gas masses from mergers, accretion, star formation, supernova feedback. You can explore different population synthesis models. We have models for black hole seeding, reionization feedback, different FSK prescriptions, chemical enrichment, and dust. And if you're interested, these are all of the papers in which this model has been published recently. And so what I would just like to show you is what does this model imply, or how can we use these kinds of models to interpret the black holes which we are beginning to see in the first billion years with the James Webb. So here I'm showing you the black hole mass as a function of cosmic age, or as a function of redshift if you prefer. All of these black holes are pre-James Webb. With the Uncovered survey in which I did this calculation, these are 3 black holes that we have found really in the first billion years. So now you can see the key problem is that we are finding black holes which are of the order of 10 to the 8-ish solar masses at redshifts above 8. These are more massive than any other black holes we have. Well, we have never seen black holes at these early cosmic epochs. But we were certainly not expecting these sorts of heavy black holes, because the key issue is the following. If you take a stellar mass seed, so this is from population 3 stars, so the seed mass would be of the order of 100 solar masses, allow it to grow at Eddington, you would not reach these masses which we are observing. To be able to reproduce these black holes, you need to start from really heavy seeds, which are of the order of 10 to the 4 solar masses at a redshift of 50, and allow them to continuously grow through Eddington accretion. And so this basically is posing quite a puzzle for our theoretical models, because every black hole that we seem to observe at high redshifts is really obese as compared to our standard expectations. The problem gets worse because when you look at the volumetric luminosity function, that poses a whole new challenge. So this is the number of black holes per co-moving volume as a function of the volumetric luminosity at a redshift of 4.5 to 6.5, 6.5 to 8.5. And what you can, the upper limit that I'm showing you, so these are observations from the Uncovered survey. And what I already want to anticipate is that these are a really specific kind of black hole candidates. These are spectroscopically confirmed, but they are something which are called little red dots. So you might have heard of these, but this is a really specific class of black holes at high redshift. This is not all of the black holes that we have. This is a subpopulation, which is about 20% of all of the black holes we should have at these levels. The upper limit that I'm showing you is purely analytic. Take a halo mass function, scale it to get the right stellar mass function at these redshifts, which we know. Use local relations of the black hole mass to stellar mass to populate each of those halos with a black hole. Assume each of those black holes is accreting at the Eddington rate continuously. So an active fraction of 1, duty cycle of 1, which basically gives you this upper limit on the volumetric luminosity function. You can see at a redshift of 7-ish, we are really, the observations of these little red dots are really starting to hit against the ceiling, because this is, as I said, this is a subpopulation of the total number of black holes that should exist at these early epochs. So we just have black holes that are too many in number for their luminosity. And remember, this is really an upper limit, an upper ceiling that theory is predicting. Things keep getting worse when you look at the relation between the black hole and stellar masses. So here I'm showing you the black hole mass as a function of stellar mass at redshift 5, 7, and 10. All of these points that you see are those that I've compiled from all of the data that we have so far from James Webb. The lines that you see are the black hole mass stellar mass relations in the local universe. So in the local universe, when you look at black hole to stellar mass ratios, they are of the order of 0.1% or so. Here, we are beginning to find objects which are showing black hole to stellar mass ratios which are as high as 30 or even 50%. This is not something we have ever seen in the history of the universe. So now the problems are, why do we have black holes that are so massive compared to the host galaxies that they are living in? Is this because black holes have been, for whatever reason, overly efficient in merging? Black holes are somehow able to grow more efficiently than their hosts. So the black hole is growing, but the host can just not form stars. Maybe this is the initial phases in the growth of heavy seeds. Maybe there is more stellar mass, but we just do not see it. This is slowly getting ruled out as we follow up these fields with ALMA. Or baryons could actually exist in the right amount, but for whatever reason, they are just not forming stars. So these are all possibilities that remain completely open. And I would just like to show you one calculation, which is, again, black hole mass as a function of stellar mass. This is for a black hole at a redshift of 8. And here, the black hole, so you can see that the stellar mass is 10 to the 9, black hole mass is of the order of 10 to the 7.5 at a redshift of 8. This is already extremely high. what we had predicted pre-James Webb is these dark blue data points. To be able to reproduce this object, you can make do with it in semi-analytic models, but what you need to do is really invoke a model in which you start from really massive seeds, and these seeds can always grow efficiently. So there is no effect of feedback from either supernovae or black holes on the baryonic content of these systems. So this is really the upper limit of what you would predict theoretically, which is what you would call a no feedback sort of a scenario. And so these sorts of objects are really posing a problem for theoretical models. And so perhaps there is a need to revisit the pathways for black hole seeding and growth. So here, as a function of redshift, I'm showing you the black hole mass. So this is just something we have compiled for the LISA white paper. Here, what I'm showing you is that there are three pathways that we typically consider in astronomy, which are light seeds from POC3 stars, intermediate mass seeds from heavy clusters, and direct collapse black holes, which are extremely heavy in mass. These heavy seeds from direct collapse black holes were invoked to explain these extremely high mass black holes at redshifts of about 6 or so. The black holes we're finding now lie in this completely unknown part of the parameter space. And this is going to be extremely crucial because if you look at this plot, this shaded region ranging between 10 to the 4 to 10 to the 7 solar masses at redshifts above 3 is exactly the sort of black holes which LISA is going to detect in terms of mergers. And so in the interest of time, I would just like to anticipate that the problem is really complicated because it's, again, an extremely multi-scale problem going from the megaparsec scales at which galaxies start to come together, the kiloparsec scales on which galaxies are merging, the tens of parsecs of scales of the formation of a bound binary, and the less than 1 parsec scale of the hardening of the binary at which point you will have your gravitational waves. Different models can or cannot include these processes just given the physical scale which goes from parsecs to megaparsecs. And so as of now, this is something we have compiled for the LISA white paper. Different models predict anywhere between 1 to 100 high redshift events per year will be detected by LISA. And this is purely because of the number of processes or the parts of this entire process that you are able to follow or not. So as we move towards the future, I think what I would just like to anticipate to you is that we really need next generation frameworks for these next generation facilities. So this is Astrea's 230 megaparsecs, but to really explain, to be able to interpret the data that we are going to get from facilities going from SKA to Euclid, ELT, Nancy Grace, or LISA, we need much larger simulation boxes of the order of 1.5 gigaparsecs. How do you run these simulations whilst maintaining the resolution that you need to track those low mass sources, which are the key sources of ionization? So here we are trying to use a combination of analytic techniques and machine learning to augment the resolution of simulations. Adding a lot of subgrid physics, which is emerging out. As I just showed you, we're learning a lot about the dust enrichment, black holes, gas of these high redshift systems. And of course, we need better prescriptions also still for reionization to really be able to make predictions and synergies to link together these different observables to build a holistic view of the first million years. And this really requires combining expertise from small-scale ISM physics, reionization, to the cosmological large-scale structure. The second thing that we are really trying to do is to look at the merging black holes through cosmic time. And here, something, as I just showed you, something that has been ignored is cosmological methods of coming up with black hole seeds. So for example, you could have primordial seeds which might actually grow faster or easier to produce these extremely high mass objects we are seeing. And so I would say that given the observations that we have, the theoretical framework is completely open in the kind of black hole seeding mechanisms or growth mechanisms that we need to invoke. And so this requires black hole seeding mechanisms and coupling these to galaxy formation processes, even if you invoke something which is purely cosmological. And finally, something that is becoming extremely relevant is really building a link between the large-scale topology of reionization and the key sources that are driving the process. And so this is something I'm leading for the SK Epoch of Reionization Synergy Group and the Euclid Reionization Group, where we are trying to cross-correlate the 21 centimeter signals from neutral hypergroup with the galaxy populations that we hope to detect from things like Euclid, Nancy Grace, or the ELT. And this is again a multi-scale problem, and also, but these sorts of models are extremely crucial because they form the training data sets that you need for future facilities like the SKB. So I will end here with this picture where I just try to highlight to you the multi-scale nature of this problem of reionization. I've tried to show you that galaxy 21 centimeter correlations will be absolutely crucial in shedding light on this topology and on the sources of reionization. Recent observations are yielding a number of different puzzles in terms of galaxies being extremely dusty, extremely luminous, and hosting extremely obese black holes, which are again too many. And I think what I tried to show you is just that overall, as of now, it seems low mass galaxies are the key drivers of reionization. I didn't go into this, but AGN are really only important in the end stages of reionization, and they can provide at most a fourth of the photons that we need for reionization. So I will end here, and I'm happy to take any questions. Thank you.
Well, how are you going to measure the escape factor? I mean, you have some very rough constraints.
So basically what we're doing is, at low redshifts, there is a survey called the Low Redshift Lyman Continuum Survey, where they can actually look at Lyman Continuum emitters. So this is at a redshift of 0.3. And what they are finding is that there is a correlation between the escape fraction and the dustiness of galaxies. So the less dust rich a galaxy is, the larger the escape fraction. And so this is not something we can measure at redshifts above 2 at all. And so what we're doing is we're baselining our models against these low redshift observations. And we're saying if dust physics is basically the same, and if the escape of ionizing radiation and the interplay of that with dust is effectively independent of redshift, then you can basically use those relations at higher redshifts.
A lot of the ionizations would be associated with star formation regimes that are probably much more intense, would they, than what you're observing in the local universe,
Absolutely.
calibrating against.
No, I completely agree. So I think if you want to link the escape fraction to individual galaxy properties, this is what you can do. You can say I link it to the observed luminosity in some sense, which is linked to the amount of dust that they have. Ab initio, there's no way of doing this, because we have even run hydrodynamic simulations in which we can really track the emergence of ionizing photons. And I think then the problem is that along different lines of sight, the escape fraction looks really different. And so you can either do a line averaged escape fraction, but there's no ab initio way of doing this at the scales that we need. And so I think there's a kind of convergence in the community that the escape fraction is more or less going to be a free parameter to do as you will with it. Sorry, does it sort of make sense? I mean, I'm super happy to talk more about this. Yeah.
So I also have a question about the escape fraction, which I always thought that the escape fraction, I guess it is, goes with the how dusty the medium is.
Mm-hmm.
And in your slide 10, you also showed that the escape fraction actually makes a plateau after redshift 6 or so, right?
Oh yeah, but these are observations.
Yeah.
Yes.
And and you're also saying some ALMA survey galaxies are shows that the galaxies might be very dusty. So in that case, what's the reason of this plateau there?
So this plateau is effectively because for these things, you don't really have a strong constraint. So the error bars are large, and these are sort of the averages over all of the things that you could have at that redshift. But this is a super nice question. I would urge you to not trust anything above a redshift of 4-ish or so. And this is just because, you can go up to 5 if you're optimistic, but basically all of these ionizing photons, they just do not make it far enough away from the galaxy to be visible. And so this sort of a plateau is not a real trend. I think I would probably trust these individual detections more, because this is really averaged over the population. Sorry, does it make sense?
It does make sense. And you also said the dustiness is increasing on how many supernovas that you have. But the supernovas should heat the medium and it should distract the dust rather than to create it. So why do you think that there's a supernova?
You know, so supernovae actually create dust and destroy dust. So basically, when you have supernovae, when they explode, they throw out metals. These metals can coagulate in the expanding shock wave. But then at some point, this wave will hit a denser medium, come back, and in this reverse shock, you can actually destroy dust. I'm super happy to talk more about this. This was invoked because if you do not destroy dust, you have too much dust as compared to observations of the local universe. So for example, 1987A, we found really low masses of dust. So people invoke this sort of reverse dust model to explain why this thing is not as dusty as you might have imagined. So now, when you have supernovae, you also produce and destroy dust. So generally, the dust destruction scales with how dense the medium is, because if you have a really dense shock wave coming in, it can sputter and destroy your dust. But overall, for these high redshifts, we think most of the dust growth of the dust is basically produced by supernovae. Sorry, does it make sense?
It does.
And then you had a super nice question, where you said, well, I just showed you these galaxies are super dusty, right? But look at the stellar masses of these objects. These are above 10 to the 9-ish. And I showed you most of the photons for reionization are coming from things which are actually fainter or less massive. And those things are not something we are detecting in dust. And so those things, so it's kind of converging towards a situation in which, yes, you have a lot of these star-forming galaxies. And those low mass things are not particularly dusty, because of which you might say that the escape fraction could be much higher as compared to these more massive dust-rich sources from which escape fractions would just find it easier to just emerge out. Sorry, does it make sense?
Yeah, that I can understand completely. Yeah, okay.
Yeah, good.
Thanks.
That's great.
We have a question online by Ranchen Chen. I have a question about your reionization model. How do you model the ionization fraction inside the bubble? What mean free plot sync models do you use?
Okay, so super nice question. So here we are using the underlying density field of the n-body simulation. And we're doing this on 256 cube cells. So each cell is roughly of the order of 1 megaparsec. And so you're just using the local density field to get an estimate of the local gas density. Sorry, does this sort of answer your question?
Yes.
Okay, perfect.
Amazing. Yeah.
Thank you so much for a very informative talk. I think in the reionization community, there's always a strong interest in cross-correlating, like, as you said, sources, and then pretty much the line with other lines, etc. And you also talk about synergy driven, SKA and Euclid. I think one of the kind of main challenges is like in order to do cross-correlation, we have to come from the same patch, diverse, and then also there's consideration in the farthest space too. Do you mind kind of like telling us more about your thought on like how do we do this synergy, right, to do a cross-correlation correctly so that we can get the science out? Thanks.
Such a good question. Okay, so I can give you a really short answer. So you are completely correct. So you can start two ways. You can first say, I know my galaxy population, and I can target that patch of the sky with a radio telescope. So this is, for example, something we did with the Murchison Whitefield array. So we know a patch where we have Lyman emitters, and so you don't expect to see 21 centimeter. And so we did this. We did, I think it was 30 hours. Sorry, I can look up the numbers. But you get an upper limit on the 21 centimeter emission. And so you say, if this is below the limits that you had expected, then it kind of confirms the scenario that where you have an overdensity of galaxies, those patches are reionized early. But if you want to do proper surveys, this is what you have to do. So you have to look at the 21 centimeters. So this is for laminar parameters. You can do different kinds of experiments. I'm just showing you one. One experiment which I found really interesting is you can target regions with known laminar emitters where reionization should be complete. So they should have a really low 21 centimeter brightness temperature. And you can target a similar volume or a similar patch in a region where you don't know any galaxies. And so you can then, if that region has no galaxies, so then the 21 centimeter differential brightness temperature should be much higher. And so this is something that you can actually do really easily with, for example, the SKA. If you want to do cross correlations to get a signal, this is what you have to do. So this is the 21 centimeter Lyman alpha cross correlation. And this is on a typical scale of about 4-ish megaparsec, 5-ish megaparsec. So this is the scale on which we have the best signal to noise ratio. And here, this is the field of view that you would need to survey. So now this is matched to say what field of view would you need to observe in both your galaxies plus your 21 centimeter to have a correlation. So you can differentiate between something which is half ionized, 75% ionized, 90% ionized. So you can see if you survey really small volumes, all of these, because of a combination of short noise, instrumentation noise, all of these patches, they basically overlap. You can differentiate these things on scales which are a few tens of degrees squared. And so this is something, for example, you could do with the with Subaru or with the Nancy Grace. But this is for Lyman alpha emitters which are of this sort of luminosity. This is not something you can do with Euclid. Euclid sees much brighter. And so you can compensate for having fewer Lyman alpha emitters by looking at larger fields of view. I mean, it's not a one-to-one, but these are the sort of experiments we're trying to do to figure out what volumes to what depths do you need to probe to really be able to see these cross correlations. Sorry, does it make sense? Perfect.
So the SKA is a multi-headed beast, and it has precursors and, so on. So what part of it has to work on what time scale for you to be able to do this?
So this is for SKA phase 1 with the parameters that we had 2 years ago. So this is for a certain configuration of the core, for a certain number of antennae in the core, so you can reach your right signal to noise. If that goes through, with 1,000 hours of integration, you will be able to do this. 1,000 hours of SKA integration, SKA1. We haven't tried this with SKA2 because we don't really know what the final experiment is going to look like.
Will the experiments, is there some feedback between what you discover with phase 1 and what you go do with phase 2? Or is it locked in stone? We're going to build this. Whatever.
It's not. So the instrument design has changed a lot, and most of this has been because of budgetary constraints. Yes, I'm really sorry. I'm happy to chat about this offline. But the core has been thinned a lot, both because of budgetary constraints and also because of issues with how we're going to actually collect and process the data. And so as of now, this is the final setup that we have for SK1, but that has been driven by information that we had, for example, from MWA, from HIRA. And so, at some point, the filters were tuned to a reionization redshift of 10, which was driven by CMV constraints. And then as we were finding more and more of these Lyman alpha emitters, it seems reionization was shifting to later redshifts. And so there was a feedback in which these filters are now optimized at redshifts between 6-ish to 8-ish. So there is a feedback loop, and this is why we're trying to do these experiments now, so that we can say this is what we would need in terms of the instrument to be able to do the science that we need. Sorry, does that make sense?
Thank you.
Of course.
Any other questions? If not, then let's thank Pratika again.
Thank you.
Now there's time for refreshments.
Ruin your lunch with ask the questions that you didn't ask them. Then we'll be taking
Very nice.
I'm so sorry, I kept it on forever.
No, you were
Perfectly timed. It's when you talk Manor, you always feel like I don't know. You always feel like oh my God, I'm sick of hearing myself. But no, you're perfectly on time, man.
Thank you.
It was probably only in your own perception. So all good.
Hello. Hi, Lauren.
Nice to
How
see
are
you
you?
again.
Very nice to see you too.
Yeah, sorry I missed most of you.